Hello everyone. In this video, we cover several important topics, including tensors, gradients, and automatic differentiation. Why do we need tensors in machine learning? If you recall from the previous lecture, Python has its own built-in data structures, such as lists and dictionaries. However, it appears that in many machine learning and data science problems, we need to think about data as multidimensional arrays. And this is what is known as tensors. So to provide a brief definition, you can think of tensors as a unified and efficient way of organizing data to be able to work with different types of data such as tabular, image, and time series. And this allows us to integrate with mathematical operations such as matrix multiplication and even more complex operations, as well as optimization algorithms that are essential for model fitting and training. So let's dive a little bit deeper into tensors. So the simplest kind of tensor that you can imagine is related to tabular data. If you recall, we focus on the bank loan default problem, and let's say we have historical data about 1,000 borrowers, and for each borrower, we know information about income and debt. In this case, we can represent this data set as a two-dimensional tensor or matrix where we have n samples, which let's say here 1,000 borrowers by two features. And since this is a matrix, so the number of rows here is the number of samples and the number of columns here is the number of features. In other words, each feature in each column in this matrix represents one of the features that we have. And each row of this matrix corresponds to one sample or observation in the dataset. Now we can have even more complex tensors when we are working with the other types of data sets. For example, if you have an image data, each image has height and width. And then if we have a color image, we have three channels. And this corresponds to RGB, red, green, and blue. And now if we assume that we have 1,000 samples or images, this would be a four-dimensional tensor or array where the first dimension corresponds to the sample index and similarly height, width, and the channel index. Now, if we have time series data, let's say you want to predict temperature every hour during a day, then we can write this as a 3D tensor, meaning that we have the number of samples. Let's say you have information about 1,000 days, and during each day, we measure the temperature and some features every 1 hour. So therefore, we have 24 steps or time steps per day. And then for each time step, we have certain features such as humidity, wind speed, and so on. And the goal here is to predict the temperature based on these pieces of information that we have. Therefore, in this case, we might have information about 1,000 days. And for each day, we have 24 steps. And then for each step, we have, let's say, two features if you're working with humidity and wind speed. And therefore, the goal is to predict the temperature, which is the response or output in this scenario. So the reason that I presented this information is that we're going to start with the simplest case where we have 2D tensors for tabular data. But by the end of this course, we are also going to cover image data and time series data. And as you can see, in this case, we definitely have to deal with more dimensions. Just to recap what we covered, tensors can be viewed as a generalization of vectors and matrices to an arbitrary number of dimensions. And something important to consider here is that when we talk about tensors, dimension is usually called axis. So that's kind of like the technical term that we use when we are working with different libraries and packages where we use the term axis. And the number of axes of a tensor is called its rank. So if you have a scalar or single number, that's a rank 1 tensor, right? So you don't have any notion of dimension or axis. If you have a vector, like the one that we have here, which contains 1, 2, 4, then this is a rank 1 tensor because you only have one axis. And remember that indexing in Python starts from 0, so therefore this one axis that we have is called axis 0. But now we can have two axes, and this corresponds to a matrix. And something that is very important to remember is the way that we name these axes. So you can see that the one that is vertical here is axis 0. So if for some reason we want to add these elements along this axis 0, this means that we are adding these elements column-wise, right? Because each vertical line here corresponds to one column. And axis 1 is actually this horizontal line. So now if we want to add these elements across axis 1, then this means that we're going to add them row-wise. So this is very helpful when you want to retrieve information from tensors, so we know which element of which axis we want to recover. When we work with tensors, remember that in Python we work with object-oriented programming principles. And in this case, we can think of attributes or properties of these types of tensors. And 4 properties or attributes that you need to know and always check are these 4 attributes that we have here. The first thing is the type. So the type function is used to determine the type of an object. And then we have this ndim, which is the number of axes or rank. And then you have shape, which tells us the number of elements in each axis or dimension. And then we have data type, which tells us whether we have integers, floating numbers, and so on. So based on this information, we can now work with NumPy. And if you remember, we said that NumPy is a very important library in Python for scientific computing, because now we can work with what is known as multidimensional arrays or tensors. And these things are specifically called ND array in NumPy. Different libraries choose different names. In NumPy, it's called ND array. In TensorFlow, it's called Tensor, that we're gonna see in this video. So really it depends on the library with the exact name, but they all have the same meaning, meaning that we want to work with multi-dimensional arrays. And the nice thing about NumPy is that we also have a large collection of mathematical functions to operate on these arrays. So let's get started with NumPy. We need to first import NumPy, and it's very common to import as np, but this is obviously optional. You can just say import NumPy, and anytime that we have np, you just have to write NumPy. So one way to create a NumPy array is to pass a Python list into this method, which is called np.array, and you can see that now this is the NumPy array that we have. You can print the type of this object, because we are working with object-oriented programming, and you can see that this is actually coming from the class numpy.ndArray. So based on what we learned in the previous video, what this means is that there is a class that has been defined to tell us the properties or attributes and methods that they work on these multi-dimensional arrays, and this is called numpy.ndArray. Therefore, we can right now look at several attributes. That's exactly why we are not using parentheses, because we are not working with methods. We are just trying to look at some of the properties of this object or this numpy.nd array. And if you run this, you can see that we have one dimension or one axis, because this is just a vector. And if you look at the shape, you can see that we get 3, nothing. And this means that we only have one axis, and in that axis we have 3 elements, and that's exactly what we have here. We can also look at the data type, and this tells us this is integer 64 bits, int64. And this is because when we provided this list here, we provided integers. If you put floating point numbers here, then this should be also a floating point number. Just to see this, I can put this point here. So now you immediately see the difference, right? Because now this is interpreted as floating point numbers. Nothing else should be different. But when we run this cell, you can see that we get float 64, which is double precision, because precision, single precision is 32 bits, and this is double precision. That's something that in some cases this matters because you may want to reduce the precision or increase. So that's something important to know in the future. Now let's create a 2D array or tensor. And this is 2D because we are using two of these square brackets. So you can see that if we just use this one, this would be 1D. But now because we have a collection of these 3 1D arrays, this is 2D. In other words, now we have a matrix where in the first row we have 1, 2, 4. In the second row we have 3, 6, 5, and so on. And the first column is 1, 3, 2. So it's always good to practice with these and with indexing to make sure that you understand how to recover information and what each row and column here refers to. So if we just say, well, I have this 2D array and I want to look at the element placed at index 0. So instead of providing two indices, because here we have two axes, we only provided one index. And the way that this works is based on what we have here. So if you only provide one index, we're going to look at the first index or axis here, which is axis 0. And we're going to recover what we have in that first row of this matrix. Obviously, we change the matrix here. We have to look at it here. So the first row is this 1, 2, 4. And if you run this, you can see that we get the 1, 2, 4. So this is the same as saying that I want to look at the first row. However, if you want to look at the first column, which is this 1, 3, 2, the way that this works is that now you have to use two indices. For the first one, we use column because we want to choose all the elements that we have in the first axis. But for the second axis, we want to only look at the first location, which is here, 1, 3, 2. And if you run this, you can see that we get this result. Now we can again look at the attributes of this object y, or this numpy nd array. Now if we use .ndim, we have two axes because this is a matrix. And in terms of shape, now we get 3 and 3. So we have 3 elements in the first axis, 3 elements in the second one. And for this y, since we provided integers, you can see that we have int 64. However, if we use the same trick, we use these points here, then these things will be floating numbers, and then when they pass to numpy, they will be float 64. So why is this indexing axis is very important in NumPy? Because in many cases, we want to perform operations along only one of these axes. So let's say we want to add all the elements in this array y, but we want to do this along axis 0. So in this case, to just show you how this works, if we are adding things along axis 0 is this vertical axis. So this means that we are performing operations column-wise. So we are adding 1, 3, and 2, which we get 6, 2, 6, 1, which we get 9, and 4, 5, 3, which we get 12. But if we do this along axis 1, then this is a different story because we are adding things across the rows of this matrix. And we get 1, 2, 4. If we add these, we get 7. and then 365, which is 14, and 213, which is 6. And to just confirm this, you can see that yes, we get 6, 9, 12 if we do it cross axis 0, and if we do it cross axis 1, we get 7, 14, 6. Something that is very interesting here is that if you look at the dimension or the number of axes that we get when we perform this summation, now this is actually a one-dimensional tensor. And you can confirm this. If it's harder to see, you can just use dot shape. You can see that we have one axis with 3 elements, or you can use ndim, which tells you exactly we have one element. And why does this happen? The reason that this happens is that when you add across the rows or columns of a matrix, you effectively getting rid of one of the axes that we had in the original array. So we started with a 2D array, so now the result is 1D array. And in this case, since it's 1D, it doesn't anymore matter if this is the row or column because it's 1D array. It doesn't have any more notion of rows and columns. However, if for some reason you really want to keep the dimension unchanged, you have this option by using this argument keep dims equals true. So by default is set to be false. But if you set this equal to true, now you can see that we have two square brackets. And this means that now we actually have a 2D array or a matrix. And in this case, I can even use this dot shape. And you can see that it says that we have 3 rows and 1 column. And this is consistent because this is our first row, second row, and third row, and we only have 1 column. So in this case, we had a 3 by 3 matrix, and then we added everything across rows, and we get 3 by 1. So this is something important to keep in mind because although from the linear algebra perspective, we can think of a vector as a matrix with one row or column. From the NumPy perspective, this is very different. And because these shapes are different, you can see that you can get error messages if these dimensions do not match. Similarly, we can do tensor slicing. This means that if you want to look at a subset of this array Y, so what this means is that we want to look from the first axis, we want to look at everything located in the second location to the end because indexing starts from 0. And the same thing for axis 1. So therefore, what this really refers to is from the second location, so 3, 2, 6, 1, and then the same thing with here with other axis 1, you want to do 6, 1, and then 5, 3. So if you take the intersection of these two, then you should end up with 6, 5, 1, 3. Because in some sense, you have an AND operation between these two, right? So you want to choose everything that is in the second location and to the end. So this gives you this whole 2 by 3. And the same thing when you do this with along axis 1, and the intersection of the two is the 6, 5, 1, 3. And we can also use negative indices similar to Python, which is the position relative to the end of the axis. And in this case, we get exactly the same result because -2, the way that this works is that the last one is always -1. So -2 is actually this one. And the same thing with axis 1. So this is -1 and this is -2. This is the same thing as saying that we want to look at the second location to the end, second location to the end, which gives us this 2 by 2 block, which is 6, 5, 1, 3. So now let's talk about tensor operations. So when we work with, for example, NumPy arrays, linear algebra operations such as matrix vector multiplication, dot product or inner product, matrix factorization are all available as well-optimized built-in NumPy functions. And the reason that we should use them instead of writing our own functions is that NumPy is much faster because of using basic linear algebra subprograms known as BLAS. And also, these routines are usually implemented in low-level languages that you have a lot more flexibility in terms of utilizing hardware's capabilities such as vectorization, parallelism, and therefore they're much faster than using especially like for loops and so on if we write our own functions. Just to prove this or exemplify this, let's use NumPy and create some random arrays. In this case, each array will contain 1 million samples. So we have two one-dimensional arrays, and each array contains 1 million samples. Here, we don't really want to know what's inside X and Y. I just want to show you how much time it takes to find the dot product or inner product using NumPy. And for doing that, we use time module, and time.time tells you the time at that specific point. So we can just record the time right before finding the dot product and right after, and subtract the two to figure out the elapsed time. And in this case, if we run this cell, you can see that in NumPy, it takes about 0.0008 seconds. So it's super fast given that you're working with vectors or arrays that they have 1 million elements. And in order to compare this with our own implementation, let's say we define our own function, which is called our.product, accepts two vectors x and y. It's always a good idea to use this, what we call it as doc string or documentation string, which has triple quotes. And this, anything here is just considered text or comment. So it's not gonna be interpreted as code, which is really nice. You can say, for example, accepts two 1D arrays and returns the dot product. And then you can say that this is my implementation. So you can add any information that you want here. It's actually very common to make sure that you specify the inputs and the outputs that you get from your function so everyone can understand what you have done. We can also make this function a little bit fancy by making sure that we check to see whether each array that we get is 1D array, and also they have the same number of elements. So we do this with this assert here. This makes sure to have exactly 1D arrays with the same number of elements. And after that, this is very easy to implement because we have these 1 million elements. So we have to pick the first element of the first array and the first element of the second array, and then we do the multiplication, and then we keep the result in this scalar here z, and this will be updated every time when we do this multiplication by adding the result of this multiplication to the previous value. That's exactly the definition of dot product or inner product, which is the sum of the product of corresponding elements. And do not forget to return the value of z. Similarly, we can now call our own function, pass these two input arguments, measure the elapsed time, and in this case, we are reporting our elapsed time for this dot product that we implemented, and also how faster it is if we use NumPy. So in order to check that, we divide the tr with tNumPy, so that's the elapsed time for NumPy. Obviously, if this is greater than 1, this means that NumPy is faster. And if you run this, so you can see that our implementation took about 0.16 seconds, which is about 189 times slower, right? Because the NumPy runtime was 0.0008 seconds. So you see really the difference, even in one operation, that using NumPy's built-in dot product, it can really save time. And you also can compare the results between NumPy and our own implementation. You see that the difference is in the order of 10 to the power of -9. So this is really a small amount of error, and we can claim that these two are exactly identical, given that it's very small, the difference. So both approaches work very well, except that our own implementation with the for loop is really slower. We can extend this analysis to two-dimensional arrays, right? So here we create a matrix X because we have this two-dimensional array and a matrix Y. We obviously can multiply these two because the neighboring dimensions match, meaning that X is 2 by 3, Y is 3 by 2. So if we do the multiplication, the result is 2 by 2. And similarly, we can define our own matrix product, making sure that now we have 2D arrays, making sure that the neighboring dimensions match, meaning that the number of columns of the first one is equal to the number of rows of the second one. If not, we cannot do the multiplication. The result would be the number of rows of the first matrix and then the number of columns of the second matrix. And we can write two for loops to find the dot product or inner product between each row of the first matrix and each column of the second one. And in this case, this ZR is our own implementation. In NumPy, obviously, we have ways to do this. Actually, this np.dot, which we used before for dot product, is a very versatile tool. If you provide two-dimensional arrays, it automatically knows that you want to find matrix multiplication rather than the dot product between one of the arrays. However, just to make sure that this is not confusing and we use it the way that we think it's operating, it's better to use np.matmul, which stands for matrix multiplication. And in this case, this is specifically designed for multiplying matrices. Regardless, if we run this cell, you can see that all of these cases, we get exactly the same result, meaning that the result that we get is the same, but obviously you can measure the elapsed time again, like what we did before, and then the NumPy version should be much, much faster than our implementation because we use for loops, and for loops are inefficient because we have to pick elements one by one. So we cannot take advantage of parallelism or other hardware capabilities. So far we look at 1D and 2D tensors mainly, but the fact is that we can have higher dimensional tensors. And one of the ways that we can look into one of these tensors is through TensorFlow and Keras, which is a very popular deep learning library that we're going to use throughout this course. And also, this is an exercise to make sure that you can install external libraries that are not included in the Anaconda distribution. So if you have followed the instructions, you already have Anaconda and NumPy, Pandas, and so on. But you can check to see that and to make sure that you do not have TensorFlow. And this is something that you have to install separately. And if you're using Linux, Windows, or even Macs with Intel processors, installing TensorFlow is very easy. As an exercise, you go to this website, tensorflow.org, and usually it's like one line of code that you use to install that. However, if you're using MacBooks with Apple Silicon, it's a little bit more complicated, and the standard approach will not work if you try. So in that case, I definitely recommend you to take a look at this video that I have prepared. So anyways, this is a good exercise to make sure that you can install TensorFlow so that you're prepared for later lectures. And if you have any questions, let me know. So once we install TensorFlow Keras, since now we know about object-oriented programming modules and packages and libraries from the previous video, you can see that how this works. So we have TensorFlow, which is like the main library. We use this dot notation, so this means that inside TensorFlow we have Keras, and inside the Keras we have this module that contains different data sets. And inside that we have this MNIS, which is the handwritten digit data set that we talk about. And now once you import this, you can say MNIS.load data, and here you have images and their labels for both training and testing. Remember that you always need testing data in machine learning to make sure that your model generalizes well. If you look at these train labels, this is very straightforward. So you can see that we get these integers from 0 to 9. This corresponds to the digit that each image represents. And the data type here is unsigned integer 8. So this is a very easy type of data structure. You can also look at these trained images. Before we look into that, let's just look at the shape, right? And you can see that here we have 3-dimensional tensor, right? So you have 60,000 images, and each image is 28 by 28. So this is height and width. Based on what I showed you earlier, there could be another dimension here, which is the number of channels. But in this case, we only have one channel because these images and this data set is actually grayscale data set. So for that reason, we only have one channel, and that's why we can just ignore that, and we do not necessarily have to have this fourth dimension. And the same thing with the test images. We look at the shape of that, and we can see that we have 10,000 images, 28 by 28. This is very important because usually you want to make sure that you have the same type of images, so they're both 28 by 28. And now if you want to look at one of the images, we can just use one index, because remember, all these images, according to what we see here, they are located in axis 0. So if you want to just pick one, you look at, let's say, the one at index 0, and if you look at the shape of that, now this is 28 by 28. And if we plot this using matplotlib, and specifically this plt.imshow, which stands for image show, and we want to make sure that the color map is binary, so that because it's a grayscale, if we plot this, you can see that this is digit 5. And we can actually confirm this because trained images, they come with trained labels. So for each image, we have a label. So if I create a new cell here, and I put train labels 0, hopefully we get 5. And you can see that, yeah, it is actually this image labeled as 5. And if you want to, instead of working with these 3D tensors, work with 2D tensors, one thing that we can do, we can multiply these two dimensions. So meaning that instead of working with these 28 by 28 matrices, we can vectorize or flatten them and put them all in a 1D array, which means that in that 1D array, we should have 28 times 28 elements, which if you do the math is actually 784. So you can see that here we're using that reshape. We say that we don't want to change the number of samples, but for the second dimension, let's make it 28 by 28, or 28 times 28, it's better to say, so that we only have one dimension or one axis to represent each sample. And in this case, you see that we get 60,000 by 784, which is 28 squared. So in many cases, you can see that we do this vectorization because now we can use anything that we know about tabular data to solve this problem. Because once you do this reshaping, then this is not anymore image data in some sense, because it's just the number of samples, number of features. So it looks like very much like a tabular data. So it really depends on how you want to solve a problem. But one downside is that if you do this vectorization, we lose a lot of information about the image because now the neighboring pixels are not grouped together, right? We vectorize them, so we lose the information about spatial patterns in the data. So far we talk about tensors, and then we talk about tensor operations and resizing and numerical linear algebra operations. But there's one very important concept that we have to cover for this video, and that's automatic differentiation. So in general, if you remember, like when we want to solve a machine learning problem, the loss function that we have that measures the difference between true and expected values may be a function of multiple, and in the case of the large language model that we have in week 1 or lecture 1, you may have billions of parameters. Therefore, we cannot really take these derivatives individually to understand the impact of each of these parameters on the loss function to solve the optimization problem related to empirical risk minimization. And therefore, we need to extend the notion of derivatives to function that they take tensors or multidimensional arrays as inputs. And that is what we call as gradients. So a very simple example of this is that let's say you have an input where it's a vector. So it has two elements, x1 and x2. And now you define a function on this vector, which is the Euclidean norm or L2 norm squared. And by definition, this is just the first element squared plus the second element squared. So the gradient here is the vector of all partial derivatives. So the first one is the partial derivative with respect to x1, partial derivative with respect to x2. And in this case, it's very easy to find these partial derivatives because if I want to find the partial derivative of this with respect to x1, this means that x1 is variable and everything else is constant, including x2, which when you take the derivative of a constant is 0, so this term disappears, and we know that the derivative of x1 squared with respect to x1 is 2x1. So you can use the same logic, and that will give you the partial derivative with respect to x2, which is 2 times x2. And what really is important here, if we factor out these two, you see that we get this vector x1 and x2, and that's exactly x. So what does this mean? This means that if you have an input vector x that not only has 2 elements, but it can have 1,000 elements, and you define a function on this, which is the sum of the square of those 1,000 elements, if you want to know the gradient or this collective information about the partial derivatives, the result is 2 times the input vector that you have. So it extends to any dimension, and it's a very general formula, and this really simplifies the computation. Now, in this case, we solve this problem manually or by hand, but the idea of automatic differentiation that you can see in, for example, TensorFlow and Keras and in many other machine learning and deep learning libraries is that we want to find these gradients without even manually specifying the derivative formulas. For example, in TensorFlow, there is something called GradientTape, which you can use for automatic differentiation or autodiff. And why they call this tape? So it's because it's kind of like a recording tape. So what's happening is that once you start operating on x, like what we did here, meaning that you square each element and then you add them together, this is what we usually call as the forward pass. It means that you get the input and you do some transformations and some operations on them. And so this gradient tape records all of these things. And then whenever you want to find the gradient, and that's you can do using tape.gradient, it rewinds the tape and calculates these gradients using the chain rule. So this is something that is known as backpropagation, so that it shows that it's the opposite direction of your forward pass. And we're gonna later on talk about this in details, why this happens, how this happens, and what this means. But for now, we know that in many cases, especially in machine learning and deep learning, if you want to find gradients, it's very easy. You just have to define these operations on these inputs, and these libraries, including TensorFlow, has tools such as GradientTape that you can use to find gradients. So let's put this into practice. Let's import TensorFlow as TF. If you have already installed it and everything looks great, then this shouldn't give you any error messages. And in this case, we define a variable, which is a tensor with 2 elements, 1 and 4. And then the way that you use GradientTape is with this statement, which is with tf.GradientTape as tape. And then inside this, because remember this indentation here, you do your forward operations, meaning that in this case, we want to square each element of this tensor. And in this case, this is what exactly we cover. We know that since it's a quadratic function, the gradient is simply 2 times each input. So once we define this, now we can use tape.gradient, and we want to find the gradient of y with respect to x. And if we print this, you can see that we get this result, which is another TensorFlow tensor. So this is very much like the NumPy ND array, but in TensorFlow, they call it tensor. And in this case, we get 2 and 8, which is exactly 2 times 1, 2 times 4. So this is exactly as what we expected, but you can see that we never explicitly defined these gradients here, and TensorFlow was able to figure out that the gradient here is 2 times each element. Let's make this a little bit more complex by looking at something similar to a linear regression model. So in this case, we have our inputs. We can think of these as two features that we have, income and debt. And then we have two weights, W1 and W2. We use them for transforming data. And in this case, we do the transformation in terms of the dot product or inner product, meaning that W1 times X1 plus W2 times X2. And let's say the true output is 0. We use a quadratic loss function, subtract this 2, and square that, which simply gives us y squared. And now we want to compute the gradient of the loss function, which is y squared, with respect to W1 and W2. We don't do this with respect to X1 and X2, because remember, these X1 and X2 are fixed and given to us. That's part of the training data. What we usually want to optimize in machine learning are the weights or parameters of our model. So we can look at this problem here, because our y or output is the inner product or dot product between w and x. So that's the formula. Our loss function is y squared. And now we can use the chain rule. So if you want to find the derivative of the loss function with respect to w1, you can find the derivative of loss function with respect to y, and then y with respect to w1. And in this case, this is very simple because the first one is just 2y because it's a quadratic function. And this is a very simple case too, because you're finding the derivative with respect to w1. And in this case, we have this constant or fixed number, which is next to w1, which is x1. And anything here is constant because we're finding the derivative with respect to w1, which means that when you take the partial derivative, this whole term will vanish. And you can do this exact same thing. You can see that with respect to w2, the first term is exactly the same. The second term is partial derivative with respect to w2, and that's what gives you x2. So it's 2yx1, 2yx2. That's our the two values that we get in our gradients. So let's see if TensorFlow can also solve this problem. So we define our w, and in this case, you're using tf.random.uniform, which creates arrays filled with uniform numbers sampled from 0 to 1. We define our x. Our y is the dot product or inner product between w and x. You can even see what these values are. So you can see this is our w, this is our x, and this is our y. So we do the exact same thing with tf.GradientTape as tape. We have y, which is this inner product or dot product between w and x, and our loss function is y squared. Now we go outside this with a statement and we use tape.gradient. We want to find the gradient of loss with respect to w, and these are the two numbers that we get. The question is this the correct answer? And we already solved this by hand, so we know that it's 2y and the first element of x, which is x index at 0, and 2y x1. So in this case, since I didn't want to get these long tensors with all this extra information about data type and etc., I'm also converting these tensors to NumPy. So you can see how it is easy to convert a TensorFlow tensor to NumPy and vice versa. So there's something that you can easily do. And if we run this here, you can see that now we have NumPy arrays here. And the first element is 0.22, so that's exactly what we have here, and 0.58, and that's exactly what we have here. So this result is consistent with what we have in this case. This comes very handy when we talk about neural networks and deep learning models, because we have multi-layer data representations or transformations. So we do a lot of layers of transformations, and we should be able to find the gradient of the loss function with respect to these parameters. And that's usually something that can be easily done thanks to tools such as GradientTape in TensorFlow. If you want to read a little bit more about gradients and automatic differentiation, this is really important topic. Here we cover the basics. TensorFlow actually has a really nice blog or information on this that you can find in this link. I hope you found this video helpful, and thanks for watching.